So we've been looking at finding the area between two curves for the last couple classes, and today we're going to talk about, well, what happens if we take that area and we revolve it around an axis or a line. So we're going to kind of start off a little bit basic, and we'll kind of talk about what this idea is about how we actually do these revolutions. So we can start off with any function. We'll kind of take a look at a couple of different ones today. So let's say that this is our function here, and we're looking at the interval from a to b. And in this case, we're going to rotate about the x-axis. So what happens if I take this region and I actually like swing it around so that it revolves around the x-axis? What we would end up getting is going to be some sort of like three-dimensional shape like this. So if we think about what's happening, if I were to take like a knife and slice through any point or any kind of area in this solid, I'm going to get some sort of cross section. And what I mean by cross section is kind of like the face of, like, if I were to take that and like split it apart. And we're going to be talking about this cross section kind of in terms of the area. So we're going to say that we're going to let capital A of x represent the area of the cross section. So in this case, if we're thinking about what this cross section is, in the case of this problem, the cross section is going to end up as a circle. So if you kind of think about, if you take a knife and slice through it and kind of like open it up, it's going to be a circle. But the thing is we don't have just one single tiny little thin slice here. We've got a whole bunch of them taking up this whole three-dimensional area. And what we can kind of think about is, well, okay, well, this definitely has like a face, but it's also going to have some sort of height here. So if I think about this kind of like little thin piece right here as being like its height, what that actually ends up representing, and we've kind of talked about this idea a couple of times when we've been looking at the x-axis, if we know that this is representing the height of this kind of like tiny little cylinder that's happening, it's going to be a really bad drawing, so I apologize. That height, in terms of the x values here, that height is actually going to be our delta x, because that's our change in x as we kind of move along the x-axis. So here's the area of the face, and then here's our height. And in this case, the area of our face is going to be the area of the circle. Our height is going to be our delta x. So if I were to take infinitely many tiny little thin slices and fill up this solid area, what ends up happening is we actually end up with something that looks like an integral, because we know that the integral is the accumulation of area over a certain period of time. So what we can say is that the volume of this solid across a certain interval is actually going to be the integral from the x value of a, which is kind of where we started out on the x-axis, to the x value of b, which is where we ended on the x-axis. So from lower limit of a to upper limit of b, of the area. Again, the area is representing the area of the kind of face of your cross section times the height. And the height is our delta x, and we would represent that as being our dx in our formula. So the total volume of this solid of revolution, in this case about the x-axis, is going to be the integral from a to b of the area of the face times the height, or delta x. So let's see what this is actually going to look like if we look at an example. So we want to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y is equal to x squared, from the x value of 0 to the x value of 1. So we're going to actually kind of look to see what this is going to look like if I were to do the actual revolving thing. So it says to illustrate the definition of volume by sketching a typical approximating cylinder. So let's say, okay, well, this is the area that we're talking about. All this area underneath here from 0 to 1. And I want to take it and I want to actually revolve it around the x-axis. Let's see what that would look like in terms of an animation. I know this is going to be a different function that we're going to talk about, but hopefully it'll kind of help you visualize it a little bit better. So here's the area of a square root curve, but that's the idea when we rotate about the x-axis. We're looking to get a solid that's going to look like that. And again, the face of the solid is going to end up being some circular region. And again, the height is going to end up being our delta x, or the change in x over that entire interval that we're talking about. So let's use this idea on our example. So if I were to think about this as being kind of a rotation, well, I'm going to have like my curve start up this way and I start rotating it about the x-axis. It might look something like this. And you can kind of think about this as being like a three-dimensional solid. Again, my drawings are really not accurate today. And any cross-section that I'm going to get is going to be some sort of circular region. And again, I can kind of add on a little bit of a height if I wanted to here, which again would represent the delta x. So using the idea of what we were talking about with the volume as being the integral from A to B of the area of the cross-section times delta x. Well, let's talk about the area of this cross-section. So if I kind of pull this circle out, well, the top of the circle is going to be kind of representing this x squared. And what I want to know is, well, okay, if I wanted to find out what the area of this circle region is going to be, if the top is our x squared part and the center were to be on our x-axis, no matter where I were to draw a cross-section, the radius would just be the distance from the x-axis up to that curve. If I were to move it over a little bit and make my circle a little bit larger, my radius is still going to be the distance from the x-axis up to the top of the curve. So here, the radius, if we kind of think about this in terms of like how we were integrating from top minus bottom, well, our top of our radius is just our x squared function. Our bottom is actually just the line y is equal to 0. So our radius is actually just going to be this x squared minus 0 to get the radius here. So the area of this cross section would be pi. And our radius, again, is just going to be this length from this x squared down to the x-axis. So in this case, that's going to be x squared squared. Because again, the radius is just the distance from 0 to x squared, which is just going to be x squared. And remember that the area is going to be pi r squared. So if this is our radius is x squared, we also have to square that. So if we kind of simplify that a little bit, that's going to be pi times x to the fourth. And the x values, because remember that a and b represent x values, the x values that we're looking at are the x value of 0 to the x value of 1, because it's telling us that right in the problem. So I'm going to say that my volume is going to be from the x value of 0 to the x value of 1. I'm going to go ahead and put in my area, again, of this cross section here, the area of a circle. So pi times x to the fourth dx. Again, the dx is representing our height across this entire interval. And remember that with any constant, we're allowed to pull that on the outside of an integral. So this pi is actually a constant that we can get on the outside, so that we're only really doing the antiderivative of this x to the fourth piece. So what we're really doing is we're taking the antiderivative from 0 to 1 of x to the fourth dx, and then we're going to be multiplying it by our pi. And here's where our calculator can kind of help us do this calculation pretty quickly. I'm just going to go ahead and integrate from 0 to 1. Type in my x to the 4th dx. Hit enter. That's going to be 1/5. But again, that 1/5 is going to be it's going to have to be multiplied by the pi. So that actually means that the area of this region, if we were to take this x squared curve and rotate it about the x-axis over the x value of 0 to the x value of 1, the area of that, or the volume of this solid is actually going to be pi over 5. So let's take a look at a couple of more examples, and you'll kind of see that this pattern actually holds for what we're going to be talking about with the next couple of examples with the x-axis as well as ones for the y-axis. So the next one, I actually already graphed this curve in just to kind of save some time here. So we're looking for the volume of the solid obtained by rotating the curve y is equal to the square root of x about the x-axis from the x value of 0 to the x value of 4. So if I were to take this region and again rotate it about the x-axis, this is kind of like the animation that I'd showed you before. If I kind of translate these points down here, the other part of my curve is going to look something like that. So if I think about this as being like a revolution about the x-axis, I'm really thinking about this like part as being a solid. I'm really only worried about the x value of 0 to the x value of 4. So I'm really only worried about this chunk here. So 1, 2, 3, 4. So this is really the area that I'm wanting to calculate, or the volume. I don't know, I keep on saying area. So again, if I think about this as being a circular cross-section, which is generally going to happen here, my radius of my cross-section, again, is just going to be the distance from the 0 up to the top of the curve, or top minus the center here of 0. Well, the top is still just this curve, the square root of x. And it doesn't matter where on that curve I am, the top is still going to be the square root of x no matter what. So the radius is just going to be the square root of x minus the center point, which again is just 0. So if I think about this as, again, being a circular cross-section, my area is going to be pi times my radius squared. And again, my radius is just the square root of x, because that's going to be the distance from the top down to the center point of 0. So square root of x squared. If I kind of simplify that a little bit, that actually is just going to give me that my area of this circular cross-section is going to be a times pi times, or a is equal to pi times x. So if I want to calculate what the volume is, well, I know what my x values are because I'm going from 0 to 4. My area is pi times x dx. Again, the pi is just going to get taken out as a constant. So I'm really just left calculating the antiderivative, or the integral from 0 to 4 of x dx. Again, I can do that by hand, but I can also use my calculator to just kind of speed things up a little bit. So 0 to 4 of x dx is going to be 8. But again, I need to make sure that I am also bringing along that pi that we carried along on the outside as being a constant. So that means that this is going to have a volume of 8 pi. All right, look at one more example. So we want to find the volume of the solid obtained by rotating the curve x plus 2y is equal to 2. I put that in slope-intercept form to get the graph of what that's going to look like. And we want to, again, rotate about the x-axis, and we're bounded by x is equal to 0 and y is equal to 0. So that really means that of this line that I drew here, I'm really concentrating on kind of that piece inside of there. So x is equal to 0 and y is equal to 0 is going to be kind of bounding this area right here. So that little triangular area. So if I think about this area as being rotated about the x-axis, I'm going to get something that probably looks like a little triangle. again, if I think about this as being a solid, again, it's going to have a circular cross-section as long as I'm rotating about the x-axis. So if I think about what's going on here in terms of the area of my cross-section, still circular, so it's still going to be pi r squared. What's my radius? Well, my radius, again, is just the distance from the top to the center point of the circle. So the center of the point of the circle is still 0 because we're still lying on that x-axis. The top point is still just my curve. And my curve is this x plus 2y is equal to 2. I guess I probably didn't leave myself enough room here. But since we want to integrate in terms of x, since we're going from this to here and we're doing top minus bottom, I want to make sure that my equation is in terms of x. So it's got to be in a y equals form in order to use that to plug in for the radius. So here our radius is actually going to be 1/2 x plus 1 quantity squared. So if I want to calculate what my volume is, so I know I'm starting at the x value of 0. If I look to see what my x-intercept is over here, my x-intercept is going to be 2. So I'm looking at the x value of 0 to the x value of 2. And then I'm going to go ahead and put in my area of my cross-section, so pi r squared times delta x. We'll pull out that pi. And I will use my calculator to help me calculate this. So 0 to 2, negative 1/2, 1/2, x plus 1, quantity squared, dx. That's going to give me a volume of 2/3. But again, we need to multiply by that pi. So the volume of this region being rotated about the x-axis would be 2 pi over 3. So again, if we're thinking about the area of the cross-section, we want to know what its radius is. And generally, the radius is going to be your top minus kind of your center point of your radius, which in this case is just going to be 0. So let's talk about what happens if now we want to rotate about the y-axis instead of the x-axis. Well, if you can kind of imagine what we've been talking about with the area between curves, if we're rotating down about the x-axis, we were rotating with respect to x, or we were integrating with respect to x. If we're rotating about the y-axis, now we probably want to integrate in terms of y, since we're talking vertically here. So we want to find the volume of the region enclosed by y is equal to x squared, x is equal to 0, and y is equal to 4 when it's revolved about the y-axis now. So again, I just kind of sketched in this curve y is equal to x squared. I know I'm bounded by x is equal to 0, so that's why I kind of didn't draw the other half of my parabola, because here's the line x is equal to 0. And I'm also bounded by the line y is equal to 4. And this time I'm rotating about the y-axis. So instead, I'm actually going to be rotating this way. So my three-dimensional solid is now no longer going to be kind of facing this way. We're now going to be facing this way. So if I think about what's happening, if I take this branch of my graph and I rotate it about the y-axis, well, I'm going to have some sort of symmetry going over here on the left side. And then my cross sections are still going to be circular, since we're still kind of rotating it around in kind of a circular fashion here. But now the radius is going to be a little bit different, because now the radius of this circular cross section is no longer going kind of up and down. The radius is now going, I'm going to say right to left, because that's kind of how we thought about the area between two curves when we were integrating in terms of y. So if we think about what the right-hand side of this curve is, well, the right-hand side of the curve is just the y is equal to x squared. But because we are rotating about the y-axis, we're going to be wanting to integrate in terms of y instead of x. So when I go to use my radius, I'm going to want to manipulate this equation as an x equals instead. So I'm going to go ahead and say that this is going to be equal to the square root of y. So this is technically x squared, but if we solve it for an x equals equation, it's really the square root of y. So this is really my right-hand part here is really the square root of y. And then if I think about what the center point of my radius is here, well, the center point is still 0, a y value of 0. I'm sorry, an x value of 0. So my area is still going to be circular. It's still going to be pi r squared, but now my radius is now going to be right minus left. So my right side, again, is this curve, but it's going to be written in terms of an x equals equation, so in terms of y. And over here, my x value is 0. So my radius is going to be the square root of y minus 0, which is just going to be the square root of y. So if I want to think about what the volume is going to be, here, my general volume formula for rotating about the y-axis is now no longer going to be a to b, because now we're not talking x values, we're talking y values. We're going to say it's from c to d. And now we're going to be talking about it in terms of y. Because if we think about what the height would be of this solid, or this kind of little piece of this solid here, we before said it was delta x, but now it's going to be delta y, because this is a change in y values instead of a change in x values. So our volume is now going to be a y value of c to a y value of d, area in terms of y, dy. And again, here's my area in terms of y. And if I were to kind of clean that up a little bit, this is really going to give me an area of pi times y. And if I translate that over here into my volume, well, now I'm talking a y value to a y value. Well, my bottom y value here is 0, and then it's telling us that my top y value is going to be 4. So we're going to be integrating from the y value of 0 to the y value of 4. Again, my area is pi times y times dy. And I can do the exact same thing. I can pull out that pi as being a constant. And again, I can just go to my calculator to actually do that integration here. And again, even though we're integrating in terms of x on or y on our paper, I'm going to integrate in terms of x on my calculator. So again, that's going to be 8 times our constant of pi. The volume of this solid rotated about the y-axis from the y value of 0 to the y value of 4 is going to be 8 pi. Okay, let's look at another one. So let's find the volume of this region enclosed by x is equal to negative y squared plus 4 and x is equal to 0 when it's revolved about the y-axis. So again, just to get the graph, I did write this in terms of y equals, just so that I would be able to kind of graph it to see what the actual function is going to look like. It would continue on this way. The reason that I did not continue on that way is because I know that I'm bounded by x is equal to 0. So I know I'm cutting my graph off right here. And I'm revolving this about the y-axis. So again, it's going to be kind of going this way in our circular fashion. So if I think about kind of the symmetry that's going on here, my three-dimensional solid might look something like this. Here's kind of my circular cross-section here. Again, the radius is kind of going horizontal now. So if I think right minus left here, or right minus the kind of middle point or the radius point here, or the center point here, my right function, again, is just this square root function technically. But again, since we're rotating about the y-axis, we're going to want it in terms of an x equals equation, which up here it nicely is already written out for us in that fashion. So my area is still going to be a pi r squared, because it's still a circular cross section. But now my radius is going to be my right minus kind of that center point. The right function again is just this curve, which in terms of y is negative y squared plus 4. And again, minus the center, which is just going to be the x value of 0. Which again, I could clean this up if I wanted to. This would require some foiling out, so I'm actually not even going to bother doing that. I'm just going to go straight to my volume. And if we're thinking about what the y values are here, the y value is actually going to be this minimum point of -2 to this maximum point of +2. And then I'm going to go ahead and plug in the area. And then factor out that constant of pi, which you can do that in this step if you just kind of get the hang of doing it kind of as you're plugging in everything else. So you don't have to write it out as a separate step every single time. And then I will go ahead and use my calculator here. So -2 to 2. The quantity of negative x squared plus 4 squared dx, which is going to be 512 over 15 times pi, which will give us a total volume of 512 pi divided by 15, which we could get a decimal approximation if we wanted to, just to see what that would look like, about 107.233. All right, we'll look at one more. So now we want to find the volume of the region enclosed by x is equal to y squared plus 2, x is equal to 0, y is equal to 1, and y is equal to 2 when it's revolved about the y-axis. So again, this equation I just wrote in terms of y so that I was able to kind of get what the graph looks like. I didn't put in my other boundary lines yet. So my other boundary lines are x is equal to 0. So over here. Y is equal to 1. And y is equal to 2. So it really looks like the region that we're capturing is going to be kind of this little like thin slice in here. So that's what we would want to revolve about the y-axis. So just to kind of get a good idea of what that's going to look like. Maybe something like this. Again, I don't really have much room to draw in like kind of a cross section, but if you think about like that almost might look like a UFO type deal if you kind of think about that in 3 dimensions. So our cross sections again are going to be circular. And again, if we think about our right minus left, so if I were to take a circular region on the inside of here, our right function is this technically square root function, but again, in terms of y is going to be this y squared plus 2 function. And then my radius center point, again, is just going to be 0. So my area is still going to be pi r squared. We're still dealing with a circular cross section. And the radius is going to be right minus left. So our right is going to be y squared plus 2. Our left would just be 0. Y squared plus 2 minus 0 gives us this radius here of y squared plus 2. So then when I go ahead to find my volume, the y values that we're dealing with are actually written right here, 1 and 2. And I'm actually going to go ahead and factor out that pi in my first step. So that's going to be y squared plus 2 quantity squared dy. And again, you could expand that out if you wanted to. I'm just going to use my calculator here. So 1 to 2, x squared plus 2 squared dx. So it looks like it's going to be 293 over 15, again, times pi. So 293 pi over 15 is going to be our volume when we revolve that about the y-axis. All right, so now we are going to look at the washer method, which is, well, what happens if we have some space here? So what happens if we don't end up getting a solid disk? But that's going to be in another video. So I'm going to have you guys do some homework and try some of these problems and let me know if you have any questions.